Enthalpy changes are heat changes accompanying physical and chemical changes. Actually, an enthalpy change is the difference between the sum of the heat contents of products and the sum of the heat contents of the reactants. So you have something like this. Delta H is the sum of the difference between the enthalpy of the reactants and the products. So let's say this is the enthalpy of the reactants, of the products, minus the enthalpy of the reactants. That will give us the change in energy. Now the units, that's the unit of enthalpy change, or the unit of enthalpy, is kilojoules per mole, or in some cases you find it as kilocal per mole. All right, now there are basically two types of enthalpy changes. All right, the first one we call that exothermic changes, and the second is called endothermic changes. All right, now for exothermic, that is when the heat is liberated to the surroundings. So the material or the container becomes hotter than it should be. So it gives out heat. So by the time you touch it, it feels hot to the touch. Examples of processes that can be termed as an exothermic process, you have number one, which is burning. When you burn something, or when a material or a substance combines with oxygen or burns in oxygen, then you can talk about that. You can also talk about dissolution of substances. When a substance dissolves in water, that's also exothermic. Now let's talk about endothermic processes. Or changes. Now for endothermic, heat is usually absorbed. All right, heat is usually absorbed. So you have your container. It will feel cold when you touch it. It will take heat from the surroundings. So let's just have the arrow like this. So it absorbs heat from the surroundings. So for this now, the energy, which is the delta H, the enthalpy at the end of the reaction, will be more than the enthalpy at the beginning of the reaction. So the products will be at a higher heat energy level than the reactants. And typical examples of processes that go through this, you have when you have sodium chloride react with ammonium chloride. No, sorry, just an error there. When sodium chloride dissolves in water, that's an endothermic process. Or when ammonium chloride dissolves in water, That's also an endothermic process. Now, how do we go about the notation for endothermic processes? Remember, for exothermic, the energy levels, heat energy levels of the products is lower than that of the reactants. But then for endothermic, the energy level, heat energy level of the products is higher. All right, so exothermic will feel hot when you touch the container, and endothermic will feel cold to the touch. All right, so let's say we have a thermochemical equation. So how do we show endothermic and exothermic processes with an equation? For example, let's say we have water, that's hydrogen reacting with oxygen to produce water. In this situation now, all right, we can say that delta H, which represents the enthalpy, equals minus 242 kilojoules per mole. So for every mole of water formed, you have an energy of minus 242. One thing we need to state here, if it's endothermic, then your values will be positive. If it's exothermic, if the equation is exothermic, then your heat energy will be negative. So based on that fact, this guy is negative. That tells us that that equation is exothermic. One more example. Let's say we have carbon reacts with oxygen to produce carbon dioxide. All right, and let's say this is delta H, and that is minus 393 kilojoules per mole. So for every mole of this reaction, you have an energy of 393 kilojoules per mole being released. So 2 moles, that would be times 2 of that. 3 moles, that would be times 3 of that. So this is for exothermic. Let's write down an equation that shows an endothermic process. The other way around, let's say we have water splitted into hydrogen and oxygen. And at the end of the day, our enthalpy, which in this case is endo, that means heat is absorbed. All right, I said this is 286 kilojoules per mole. Another example, you see, if you just let me show you something. If we turn this around, like you see, like I explained earlier, this will be positive. The same, will be negative. The same value. All right, the same value. So you tell me which one is exothermic and which one is endo. Yes, this is exo, negative, and this is endo. This absorbs heat. As simple as that. Now let's talk about reaction profiles. Now on the right, you have endothermic changes. So this explains endothermic changes. Now if you check this particular diagram, you'd see that, let's say our values here, we've got 0, and then we've got 0 here on both axes. All right, and you have the reactants at this particular level. This is the energy level of the reactants, and then the energy level increases where you have coagulations, successful coagulations, and then you have the transition state. The transition state here, this is where the reactants changes to the product. All right, that transition state here is also called the activated complex. All right, and then the amount of energy required to move from this point, the initial enthalpy, up here, that is referred to as the activation energy. All right, the activation energy is the amount of energy, minimum amount of energy needed for successful conditions for a reaction to go into completion. All right, now after the transition state, you can see where the energy, the final enthalpy is. So at this point, the energy level of the product is way higher than what you have for the reactants, and this tells you that the product has absorbed, or let's say the reaction has absorbed energy from the surroundings. So this would be positive enthalpy. Now let's move down to the left where you've got exothermic. Now it's just the same thing, but then the only difference here is that the energy level of the products is way lower than what you have for the reactants. All right, so that's the drill here. The reactant starts at a higher, much higher energy level, and then reaches the transition stage, which are referred to as the activated complex. And from this point up to this point, that's the activation energy. I defined that earlier. And then your products, you can see that has a lower energy than the reactant. It means that there has been a loss of energy. All right, so you have that for your products right here. So if you're asked to draw and explain a reaction profile, and that's just what you have on the screen. So on your left, you have the reaction profile for exothermic reactions, and then on your right, you have the reaction profile for endothermic changes. All right. Now, enthalpy changes are usually described by the type of reaction or physical change involved. We start with the heat of formation, which is this. And that's the symbol. And then we have the heat of combustion. We're still going to refer to all of this as time goes on, but just to give you a head start into what we're dealing with. Up next, we have the heat of solution. We also have what we refer to as the heat of neutralization. Then we have what we call bond energy, or in some cases you find it as bond dissociation energy. Now, you need to know something, and that's the fact that the standard heat of a reaction is the amount of heat liberated or absorbed when the molar quantities of the reactants react together under standard conditions. For example, if you have carbon reacting with oxygen to give you carbon dioxide, which is an exothermic reaction. All right. Now, if you want to put this in a standard format, you would say that you've got 1 mole of carbon. All right. When 1 mole of carbon reacts with 1 mole of oxygen. Now, 1 mole of carbon is 12 grams. Reacts with 1 mole of oxygen, which is 32. Oh, I wrote 33. That should be 32 grams. To form 1 mole of carbon dioxide, which is 44 grams, under standard conditions. Then 393 kilojoules of heat is liberated to the surroundings. So that's the interpretation of what you have there. All right, now the principle guiding changes in enthalpy and all of that is called Hess law of heat summation. Summation. And what does that law, what does it say? Very simple. It states that the heat change of a chemical reaction is the same whether the reaction occurs in a step or several steps. All right. Another interpretation of that is the fact that the change in enthalpy is independent of the steps taken. For example, let's say you've got A. So step 1 goes to B. And then you have A. This is another step going to C. So let's say, now, this is the main reaction, A to B. But the reaction could take other pathways. Let's say we have another pathway. So this is 1. This is another pathway to D. And then you've got the last pathway. Let's see, is B to D. That's H3. Now, what his law is saying is that the major energy change, or enthalpy change, as you might want to call it, which is this, Now, this is overall, all right, is equal to the first guy and the second guy. That's the second enthalpy, the second step, plus the enthalpy for the third step. Yeah, and that's what Hess law is saying. All right, and you should take note that Hess law is based upon the first law of thermodynamics. All right, we've got a question here. It says determine the heat of formation of carbon monoxide from the following thermochemical equation. You have the first one, and then you've got the second one. Now, what we need from here is carbon reacting with oxygen to give us carbon monoxide. Alright, and this is gas. So we're required to get the heat of formation for this. So how do we do that? How do we get that figure? Now we'll name this equation 1 and then equation 2. We'll reverse equation 2. Now we do this so that we can add both equations. So let's reverse equation 2 and see what we will come up with. Let's say we've got equation 1, which is carbon reacting with oxygen to give us carbon dioxide, and then the heat of formation for this is minus 393 kilojoules, and we'll reverse the other one. This is equation 1. Let's reverse equation 2. The product will become the reactant, and that's just what we mean here. And then you have CO, which is gas, carbon monoxide, plus oxygen. All right, going into that should be lowercase subscript, in fact. Now, since you've reversed the equation, minus 285 kilojoules will turn to positive 285 kilojoules. So once you've reversed the equation, it will change from exothermic to endothermic. All right, if the equation you reversed was endothermic, positive, by the time you reverse it, it will change to exothermic, negative, in terms of the energy change. All right, that is settled. Now, the next thing we'll do is we cancel the species that appear in both equations. So we have carbon dioxide appearing in both equations. We cancel. We have oxygen appearing in both equations. We cancel. And that's it. And then we add these guys. So by the time you do that, let's write down our final equation. Final equation, we have carbon sorry, just a moment. Okay, carbon plus oxygen, that gives us carbon monoxide. Okay, that gives us carbon monoxide. And 3 minus 393 plus positive 285 kilojoules. That will give you minus 108 kilojoules per mole. Per mole. Yeah, per mole. Alright, so with that setting, now let me show you a different way by which you can solve this same question. Alright, we can decide to solve the problem schematically. So what do? We let x represent the change in energy of formation for carbon monoxide. Alright. Now the x is what we need. We don't know the value. So what do? We'll apply the principle of additivity. We know the overall change is minus 393. Alright. Now, the smaller steps you have, if you're to add those ones, they should give you what you have for the overall. So since we know what the overall is, and we know what one of the step, the energy change for one of the step, that's minus 285 kilojoules. You have that right here, and this will be equal to minus 393 kilojoules, and x here will be minus 108 kilojoules per mole. So that solves the problem right there. So we're told to calculate the heat of formation for the oxidation of carbon monoxide to carbon dioxide. So what do we do in that case? First things first, we know that the heat of formation for oxygen equals 0. So in the ground state, it equals 0. And we'll apply the equation, which is the sum of the heat of formation for the products minus the sum of the heat of formation delta. You've got delta there, which means change, all right, for the reactants. And in this case scenario, you can say the heat of formation for carbon dioxide minus the heat of formation for carbon monoxide plus the heat of formation for oxygen. Now we've added 1/2 there, half, which shows the number of moles we have there. All right, so you have to plug in the number of moles. That is very important for your calculations. All right, so we plug in the numbers here. So this is equal to, let's substitute the values. Heat of formation for carbon dioxide is minus 393 kilojoules per mole, and that's for the products. Now for the reactants, the heat of formation for carbon monoxide is minus 108. So we've been given that from the question, plus the heat of formation for oxygen, which is 0, and that's the ground state. And then you compute this. This is minus 393 minus times minus, that is plus, is 108 kilojoules per mole. Now, this gives you minus final answer, that's minus 285 kilojoules per mole. Now let's talk about the heat of combustion. The heat of combustion is the heat liberated when 1 mole of an elemental compound is burned completely in excess oxygen. Emphasis on the word completely. So in this case, you can determine the heat of combustion by using an apparatus called the bomb calorimeter. Alright, so the heat evolved in that experiment is known to cause a rise in a certain mass of water or mass of substance will cause a rise in the temperature in that calorimeter. So the heat lost, which causes a rise in temperature, is usually measured, and then you can use that to get your heat of combustion. So the heat loss in this case is equal to the mass of the substance multiplied by a specific heat capacity and the change in temperature. So this is heat loss, which is measured in kilojoules per mole. You've got the mass, which is measured in kg, and in this case we can have the measurement in grams. All right, specific heat capacity of water, which is 4.2 joules per gram per degree Celsius. And that is if you're working with grams as your mass. But if you're working with kilograms as your mass, that would be 4.2. So that would be 4,200 joules per kilograms per degree Celsius. Okay, so temperature, you measure that in degrees Kelvin, degrees Celsius or Kelvin. So you have a question here that says 0.32 grams of methane raise the temperature of 100 grams of water in a bomb calorimeter by 80 degrees Celsius after burning completely. What is the heat of combustion of methane as obtained from this experiment? So you have the specific heat capacity given to you. Now methane has the chemical symbol for methane is CH4, and you get the molar mass, that is 12 for carbon, and then hydrogen, that's 4 multiplied by 1, and that gives you 16 grams per mole for methane. Now let's check how many moles of methane has been burnt. Number of moles of burnt methane. Remember, number of moles equals mass over molar mass. All right, good. So that will be the mass, that's 0.32 as given to us from the question, over the molar mass, that's 16 grams per mole. So this is grams per mole. That gives you 0.02 mole. Now let's convert that mole. Let's check how many kilojoules of heat has been produced from that. So the heat liberated by 0.02 moles of burnt methane, that is the equation Q equals mc theta. Now we need to get Q. We need to find Q. Well, Q is not lost. We just need to find it. So that's 100 grams of water, all right, multiplied by 4.2 joules per kilogram per grams rather per degree Celsius times 80 degrees Celsius. Now, if you decide to use Kelvin, then you change this to K, and then you add 273 K to this. All right. So that's just, and if you decide to convert the grams to kilograms, this will be 0.1 kilograms, and this will be 4,200 joules per kilograms per degree Celsius. Aha. So I just stated that because questions might change the units so that you don't get confused. So be confident with the conversions. All right, when you compute all of this, this will give you 33,336,000 rather joules, which is 33.6 kilojoules. All right, so we're not done here. This is the amount produced by 1 mole. So we need to note, okay, this is the amount, sorry. This is the amount produced by 0.02 moles. Now we need to standardize this whole thing to 1 mole. So we want to know how much heat will be liberated by 1 mole of CH4. That would be 33.6 kilojoules. Remember, this is the amount liberated by 0.02 moles. All right. So to know the amount liberated by 1 mole, you divide that figure by 0.02. That gives you 1,680 kilojoules. We have a question here on the heat of solution. Now, what does the question say? 2.22 grams of calcium chloride dissolved in 100 centimeters cube of water caused a rise in temperature of 3.4 degrees Celsius. What is the heat of solution of calcium chloride? All right. So in this case, what do we know? We know that the heat evolved when a substance dissolves in water, or the heat absorbed is equal to the mass of the solution of water multiplied by the specific capacity of the water multiplied by the temperature rise, or it could be the temperature drop. Right, so by calculating the quantity of heat evolved or absorbed by the molar mass of the solid, we can get the numerical value for the heat of solution. So we know that calcium has an atomic mass of 40, chlorine has an atomic mass of 35.5, and then the specific heat capacity of water is 4.18 joules per grams per Celsius. So whatever value the question gives you, just stick to it. All right. So calcium chloride equals 40. We need to get the molar mass, and you've got 35.5 times 2. That gives us 111 grams per mole. So we need to get the number of moles of calcium chloride dissolved. So we convert the amount of calcium chloride given to us here to moles. That's mass over molar mass. That is 2.22 grams over 111 grams per mole. That is 0.001 2 mole. Yeah. With that said, let's assume that the density of solution is the same as that of water, and that the density of water is 1 gram per centimeter cube. 1 gram per centimeters cube minus 3, or per centimeters cube anyway. Um, you have it. So let's get the number of heat, the heat liberated by 0.02 moles of calcium chloride. You know, that is Q equals mc theta, and that is 100 grams times 4.18 joules per grams per degree Celsius multiplied by 3.4. That's the temperature rise given in the question. Specific heat capacity already given in the question. The mass, which is 100 grams. We also have that, so that will be 141.2 joules, and equivalent is 1.4212 kg. Now, that is the amount of heat liberated by 0.02 moles of calcium chloride. Now the question says 1 mole, we need to get the value liberated by 1 mole. So the heat liberated by 1 mole of calcium chloride equals 1.4212 over 0.02. That gives 71.1 kg. Take note, heat liberated, heat liberation. What does this imply? Exothermic. Alright, so the heat of solution for calcium chloride here is minus 71.1 kg per mole. The heat of neutralization is the heat liberated when 1 mole of water molecules are formed from an acid-based reaction in an aqueous solution. So, the basic ionic equation is this: hydrogen ions and then hydroxide ions, giving you water, which is liquid, and then the heat of neutralization here is minus 57.3 kilojoules. Alright, in all cases, you can also write this equation as sodium ion reacting with hydroxide ion, reversible, to produce 2 moles of water in this case, and then the heat of neutralization will be the same, minus 57.3 kilojoules. One more thing you need to note, and that's the fact that neutralization is an exothermic process, and that's why you have the number in terms of the numerical figure for heat of neutralization as negative. Heat of neutralization can be classified in some situations under the heat of solution. You need to keep that in mind. So when the acid and the base involved in neutralization are both strong, the reaction involves an interaction between hydroxide ions and hydrogen ions, and then the heat evolved in that process is equal to 57.3 kilojoules in all cases of strong acids and strong bases. Now, let's say we have an example: sulfuric acid reacting with sodium hydroxide to give sodium sulfate, and water. The heat of neutralization here is minus 114.6 kilojoules. Now, why is this so? That's because you have 2 moles of water here. That is 2 times 57.3 kilojoules per mole, giving you minus 114.6 kilojoules. And that's in the case of a strong. This is a strong acid, and this is a case of strong base. Now, if you have a situation that involves a weak acid and a weak base, the heat involved in producing 1 mole of water will be less than 57.3 kilojoules. So if you have strong acid plus strong base, the heat involved will be equal to 57.3 kilojoules. But if you have a case of weak acid plus strong base, or strong acid plus weak base, the heat of neutralization will be less than 57.3 kilojoules per mole. Typical example of that is hydrogen cyanide reaction with sodium hydroxide. So hydrogen cyanide is the weak acid right here, and then this is the strong one. So you have sodium cyanide and 1 mole of water, which is liquid. So in this case, the heat of neutralization is minus 12 kilojoules per mole. If it were to be strong versus strong, that would be 57.3. So we can say that 57.3 minus 12, which was produced here, this will be 45.3 kilojoules. So here you can say that the heat of ionization, or the heat, the amount of energy used for ionization of weak acid, in this hydrogen cyanide, the energy used to ionize hydrogen cyanide is this 45.3 kilojoules. The question says 10.0 centimeters cube of 0.20 moles dm cube of ammonia solution neutralize 10.3 cm cube of 0.02 mole per dm cube HCl and liberated 102 joules of heat. Calculate the heat of neutralization of this reaction. Now, first things first, you write out the equation with the state symbols. All right, we have that stated. And the product, and that's ammonium chloride with water. Now we're required to get the heat of neutralization, which we do not know at this point. And we know this is a strong acid and this is a weak base. If you don't know what a strong acid and a weak base, or weak acid and strong base and all those terminologies, you can go back and check what they mean before continuing this video, because that is very, very key to your understanding here. All right, since we know that ammonium chloride is the weak base, ammonium hydroxide. Did I just say ammonium chloride? No, that is ammonium hydroxide. Since we know that is the weak base, and this guy will determine the extent of the reaction. So once the weak base, weak bases are partially ionizable. Same thing with weak acids. So once the weak base cannot be ionized any longer, then the reaction stops. So we need to get the number of moles for ammonium hydroxide. And that is 10.0 centimeters cube over 1000 cm cube. That's we've converted it to volume. Times the concentration, 0.2. Remember, number of moles is concentration times volume. So if you're wondering where that equation comes from, so this is volume and this is concentration. So this is 0.002 moles. All right, so what does that tell us? The number of moles for water is equal to the number of moles for ammonium hydroxide. That's what we mean when we say it determines the extent of the reaction. All right. So the heat liberated in the formation of 0.002 moles of H2O is 102 joules. All right, and that is also equal to 0.102 kilojoules. Okay, we have that already stated in the question. Then heat liberated in the formation of 1 mole of water. We subject this, that's 0.102 kilojoules over 0.02 moles, and that will give us 51 kilojoules. Since the heat is liberated, it means that we're dealing with an exothermic situation here. That is minus 51 kilojoules per mole. All right, so that will be all for this aspect.